Uh, so let us begin with lecture 1 of this course on galaxy structure. Uh, the actual title of the course is Galaxy Structure, Dynamics and Evolution, but I've taken the liberty of changing the title to Structure, Formation and Evolution, because although I will talk about galaxy dynamics, that is not going to be an area of great emphasis in this course. The reason for that I will explain in a few minutes. So this is a longer course than some of the other courses you're having. So this is a full 21 lecture course. So I will be teaching 3 lectures a week over the next 7 weeks, so as to sort of finish my lectures by the end of April 2022. So the field of galaxies is a very active field of research. That is evidenced by the number of papers that have been written in this field. So if you take last year, you'll find that if you search for papers with keyword as galaxies, about 8,084 refereed papers were published in 2021 alone. And if you take the total number of refereed papers published across all of astronomy, that is about 30,000. So more than 25% of all papers published at the current time are in the area of galaxies. And due to this, it is also true that about 25% of the astronomy researchers across the world also work on galaxies. And this is one of the largest research sub areas of astronomy. However, you'll find that if you look at India and look at how many people are doing research on galaxies, you'll find that galaxies is quite strongly underrepresented. We probably have between 5 and 10% of researchers working on galaxies, even if you include people who are working on active galaxies and normal galaxies as one category. So this situation may change in the future. It's driven primarily right now by the fact that we don't have access to very many large telescopes, and really large telescopes are needed for the study of galaxies. But as you can see, because the number of papers being written is so large at the present time, much of our knowledge of galaxies has been made in the last 20 years. So most of the things that I will talk about in this course will be based on things that were discovered only in the last 20 years. So my main mode of interacting with all of you will be via the course website, which is the URL of which is given here. So you should probably just note down, copy down this URL. I'll also send you an email with this link. If you want to reach me, then the easiest way to reach me is via email. Here's my email address, yogesh@ncra.tifr.res.in. And the PDF file for each lecture will be put up on the website immediately after it is given. So don't bother copying stuff that is already on the slide. You'll be able to download the slides whenever you want and use the material in your slides. We are also attempting to record this course. But the recording is on the cloud, etc. So it may take a couple of days before the video recording is available. That is meant only for you to review at a later stage. Or if somebody misses a class, they can go back to the video and attend the class. But don't think of it as a substitute for actually attending the class on time, because there's going to be a significant delay in putting up the videos. Course is going to be in hybrid mode. The lectures will be live from the NCRA lecture hall, where we have a full setup made here. Those of you who would like to attend in person can do so. There is sufficient space here for social distancing for about maybe 25 students. So if you wish to come, you can come here. But remote participants can also join via the Zoom link which you are using right now. We will just go around with a round of introductions. I'm just going to look at the list of participants, and I'll just call out your name and just briefly tell me where you did your previous degree from, and whether you are a student at NCRA or whether you are a student at IUCA or at the universities. So we have few students from the university sector as well. So I'd like to spend the next 5 or 10 minutes just getting to know all of you. So I'll just call out the name, and then you can please respond. Okay, so let's start with Archisman.
Yes, sir. Hello.
Yeah, go ahead, Archisman.
Yes, so this is Archisman, and I am from NCRA. I did my BSc from Presidency College in Calcutta, and then I did my first year of MSc at Pune University. I joined NCRA as an IPhD student in 2020, and yeah, that's it.
Okay, great. So yeah, so you've done you're part of our integrated program. Yes.
Right. That's right.
Okay, so the next name I see is Arpan Pal.
Hi, so I did my BSc from Bardwan Raj College and then joined NCRA as an integrated PhD student in 2020.
Okay, so you're Archishman's batchmate.
Yeah.
Yes, right. What about next name I see is Avinash Tiwari.
Yes, sir. I'm Avinash Tiwari. I'm from IUCA. I have done my BSc from Allahabad University and MSc from IIT Guwahati.
Which IIT, sorry?
IIT Guwahati.
Guwahati. Okay. Great. And you are now a regular PhD student. I think
Yes, sir.
that doesn't have
IUCA.
integrated. Yeah, at IUCA. Correct. Next name I see is Banshi Lal.
I am Banshi Lal. I did my BSc from Rajasthan University, Jaipur, and MSc from Delhi University. And then I joined NCRA as a PhD student.
Okay, great. So next name I see is Geetika Santosh.
Hello, sir. My name is Geetika Santosh. I am from outside university. I did my BSc from Newman College, Thodupuzha, Kerala. MSc from Mahatma Gandhi University, Kottayam. Presently, I am a project JRF at NSS College, Pandala. I'm attending the class in audit mode.
Okay. Just there's some names got like resorted. Just Geetika was your name, right?
Yes, sir.
Yeah. And so you'll be auditing the course. Okay.
Yes.
What are you working on your PhD right now?
Yes.
With whom are you working?
Dr. Rakhia.
Okay. Yeah. Right. Okay. Right. So the next name I see is Jyoti Prakash.
Hello, this is Jyoti Prakash, and I'm from IUCA. I did my BTech from Kusat, Kerala, and MS from JNU.
Okay.
And I joined IUCA last year.
Okay. And so so you're again a full you finished your MSc already from JP. Okay, great. So Jyoti Prakash, Jyotirmoy Das.
Hello, I am Jyotirmoy Das. I did my BSc from Jadavpur University and then joined NCRA as an integrated PhD student in 2020.
Okay, right. Great. Nilaksha Burman.
Hello, sir. I am Nilaksha, and I did my integrated MSc in physics from Tezpur University, and I joined as a full-time PhD student in IUCA.
Okay. That was Nilaksho. Next name I see is Pranjal Tambe.
Hello, sir. I'm
Yeah.
Pranjal. I did my BSc from Mumbai University and my MSc from NIT Trichy.
Okay.
And I'm from Ayuka.
Okay, great. Yeah. Next name I see is Pooja Maji.
Hi, hi sir. I'm Pooja, and I have done my BSc from Sidhu-Kanu Birsa University in West Bengal, and I've done my MSc from Banaras Hindu University, and I have joined NCRA last year.
Yes. Okay. Next name I see is Sai.
Hello, I'm Sai. I did my bachelor's from Ferguson College, Pune, and master's from NIT Sudatkal, and I have joined Ayuka.
Okay. So you're an Ayuka student. Right. Next name is Shalmuli Ghosh.
Yes, sir. I'm Shalmuli Ghosh and I've done my BSc from St. Xavier's College, Kolkata. Then I did my MSc from NIT Rourkela and have joined NCRA as a PhD.
Okay.
Yeah. Sorry if my internet connection interrupted.
Not a problem. Yeah. Thanks, Shalmuli. Next name I see is Saurabh Yevle.
Hello, sir. My name is Saurabh Yevle, and I have done my bachelor's in mechanical engineering. I have done my master's in astronomy from IIST, and I am from Ayuka.
Okay. So Saurabh is yes. Next name I see is Shiraz. Go ahead, Shiraz. Yeah. Your voice is not audible at all to me.
It's 11:46 a.m.
Yeah. We can't hear you. So I think we'll move on. Shiraz, we were unable to hear you. At the end, I'll check once again if you are able to hear us. Next name I have is Saurabh Magre.
Hello, sir. I'm Saurabh. I did a 5 years BSMS from ICER Kolkata, and I'm a PhD student at Ayuka.
It's 11:47 a.m.
Is Suwas Chaudhary.
Hello, sir. I'm Suhas Chandra, and I did my master's from IT Bombay, and I'm PhD student at Ayuka.
Okay. Next name I see is Ujjwal Panda.
Hi, Yogesh. Can you hear me?
Yes, we can hear you.
I'm Ujjwal. I did my master's in chemistry and then a bachelor's in electrical and electronics engineering from BITS Pilani. And then I joined as an integrated PhD student at NCRA in 2020.
Okay. So you had some joint course in BITS Pilani. How did you manage all this masters and bachelors all together?
So we have a dual degree program at BITS where we can take on a BTech degree along with a master's MSc degree. So I did this with 50 other people as well.
Okay.
So that's quite common at BITS.
Okay, quite a common thing. So I think I've run out of people names at least. Is there anyone I have missed out who has not introduced themselves?
Am I audible now, Shiraz?
Yeah. Shiraz, you're audible. Go ahead.
Yes. I'm from University of Kashmir. I did my BSc and MSc from University of Kashmir. Now I'm PhD student in there, and I'm currently visiting to Ayuka here.
Okay. So you are at the University of Kashmir?
Yes.
Okay. And So you are going to be at IUCA for some time, or will you be going back and joining remotely?
Yeah, when I will go back, I will join from there as well.
Okay, great. Yeah. So now we were able to hear you clearly. So if there is no one else, we will go on. So thank you for your quick introductions. I'll tell you in a minute why these introductions are important. So here we go. This is regarding the assessment that we are going to follow for this course. The majority of the weightage is going to be for 2 assignments. Each assignment will have a 30% weightage. So you'll have a 60% weightage for 2 assignments. One will be given to you at the end of the 3rd week of lectures, and one at the end of the 6th week of lectures. And you will get roughly 2.5 weeks time to hand in each assignment. The assignment is the main way in which I'm going to be able to judge how much you've understood what has been taught in the course. So the assignments are going to be a little bit weighty and difficult. They're not very easy assignments. So that is why we are giving you enough time to complete the assignment. 25% weightage is going to be for a paper presentation at the end of the course. And I'll tell you in a minute what this is all about. And 15% is going to be for class participation. Okay. And this involves both asking as well as answering questions. So I expect the class to be as interactive as possible. So those of you who want to attend in person can do so. Because we have a reasonable setup, as I said here. But if you want to attend remotely, of course, this Zoom link will be always there for you. The class participation, the more you participate, the more interactive it gets, the better you will understand. And not only you will understand, the rest of the class will also understand better. Because if have been a little bit unclear somewhere, if you clarify it for yourself, you're automatically clarifying it for others. The good news, of course, is no exams, because I think you are now too old for exams. Exams should stop at a certain level. And so traditionally, whenever I have taught this course before, I have never had exams, and I think we will stick to that pattern. The assignments gain you the majority of marks. Spend enough time on them. Some of the assignments will require some amount of computer scripting and use of some plotting software and so on. So you need to be comfortable with computer programming. So if you are not familiar with computer programming, this is a good time to learn. I strongly recommend beginners to learn programming in the Python programming language because it is very easy to learn and it's very powerful. I recently taught for the IUCA NRC program. I taught an online course of 10 lectures and 3 tutorials, which were done by Dr. Pritish Mishra on astronomical data analysis with Python. And this is the link to the web page. If anybody of you is wanting to learn Python, then this will provide a very, very quick introduction to Python programming. Okay, so now about the paper presentation. What you have to do is choose a paper to study thoroughly and give a presentation on it at the end of the course. So you can discuss amongst yourself, or you create a Google Doc or whatever, and choose a paper that no one else has chosen, and then let me know via email. If multiple people want to cover the same paper, we will need to resolve this amicably. You'll need to get in touch with me, but I'm going to give you such a long list of papers to choose from that I hope that we will not have to resolve conflicts. You should present the paper as if you wrote it yourself. So you have to be very, very thorough about what is there in the paper, and you should be able to present it. I think present it very succinctly, very clearly, and in a short amount of time. This is a skill that is going to be very, very crucial in your future astronomy career. So the earlier you develop it, the better it is. And therefore, I'm going to get you started by having you present a paper. What does it mean by you present the paper as if you wrote it yourself? What it means is you pretend you wrote it, and then you should know everything about the paper. You may not know everything about other papers that are cited in this paper, but about the paper yourself, you should have a complete understanding. So we are going to use, for these seminars, we are going to select papers from a long list, which is available at this URL. These are all publications of a very large galaxy evolution survey called GAMA, G-A-M-A, which was done with a variety of telescopes, but primarily driven by a 4-meter optical telescope in Australia. At this website or URL, you will find a long list of papers. There are more than 150 refereed papers that are there. And you will have to present a talk on one paper, any one paper, which will be 17 minutes long for the talk itself, plus about 3 minutes for questions. So do go ahead and discuss, choose a paper you like, and let me know by sending me an email by the 23rd of March, 2022. You must choose a refereed paper from the list. There are a few unrefereed papers, but please don't choose them. We have a long list of refereed papers to choose from. So despite having 20 odd students in this course, you'll still be able to find the right paper of your choice, because there are more than 150 papers in this list. Make sure when you choose the paper that the paper is not too long or complicated to explain in 17 minutes. So I have found in the past that sometimes students have chosen very long and complicated papers, and then they are unable to summarize it in time. If you feel that the paper is slightly longer than you would like, and you would still really want to talk about it, please go ahead and do so. And during the talk, you will of course be able to leave out. You can upfront say that certain aspects of this paper I'm not going to talk about, and then talk about the remaining paper. You're going to have a tutor for this course, which will be Yash Bhusare from NCRA, who is 1 year senior to you to your batch. And he's going to be evaluating the assignments, and he's also going to sit with me and help me evaluate the paper seminars. Okay, that's Yash. Okay, so now let's come to the official syllabus, and let me tell you why I don't like it. So the official syllabus as it stands was designed about 25 years ago by people in IUCAA and NCRA who are no longer here, and that course had a very strong emphasis on dynamics. So the text that you see colored in red here is something that they were working on at that time, and therefore was included. But now I think that the emphasis of the community on dynamics is relatively low. There is a lot more happening for example, in using galaxies for studies of large-scale structure, the baryon acoustic oscillations, and several other things related to galaxy formation and evolution. So what I'm going to do is I'm going to place a lower emphasis on dynamics. So we will talk about dynamics, but instead of spending 7 or 8 lectures on galaxy dynamics, I'm going to spend 1 or 2. And I'll spend a lot more time on galaxy morphology, on the chemical evolution of galaxies, and on the broad topic of galaxy formation and evolution, which is not actually usually covered in detail in previous editions of this course. Many active research topics not covered in any other course are missing from this syllabus. For example, star formation, stellar population synthesis, and high redshift emission and absorption line galaxies. These are very, very active fields of research at the present time and are likely to remain so for the foreseeable future. And therefore, I wanted to place a greater emphasis on these topics in my course, which is what I plan to do. This course has linkages to several other courses. So for example, your extragalactic astronomy 1 cosmology course would have covered quasar absorption systems, which are basically nothing but high redshift galaxies seen in absorption. In your course on the interstellar medium, you would have studied extinction and reddening of starlight and dust, and also ionized gas, H2 regions, molecular clouds, and star formation. We will, of course, while studying galaxies, encounter all of these things, but from a slightly different perspective. We will talk, for example, more about the role of the interstellar medium in feedback processes, in the starting of star formation, and also in the quenching of star formation, the stopping of star formation. So we will look at it from a different angle than the ISM course. AGNs, you have a full course on that, which will come up in the next quarter on radio galaxies and quasars. And that is focused on the phenomenology of AGNs. And we will not talk about that in this course, but again, the role of AGN feedback processes, which is very important in the evolution of galaxies, will be discussed in this course. Okay, so what am I actually going to cover? Okay, so if one were to give a very comprehensive course on galaxies, then these are the topics that one would cover. Okay, what I have done is I have sort of highlighted in bold in black color topics which I will be emphasizing quite a lot. I will be shown in red font are topics that are covered in some other course as part of your graduate school. And so although they rightly belong in a course on galaxies, since they are covered elsewhere, I will not be covering them, or if I cover them, I will cover them very cursorily in a very shallow way. For example, gas and dust in galaxies is a topic that should be covered in your ISM course. So I'm not going to talk about it. Similarly, galactic nuclei and nuclear black holes, the supermassive black holes that sit in the center of galaxies, and the topic on active galaxies and quasars is something that is going to be covered quite extensively in your course on AGN. So again, I'm not going to cover it in detail. The cosmological framework itself we will use while studying galaxy formation and evolution, but we are not going to do the cosmology itself or the early universe and things like that. Those are going to be covered in separate courses. Again, reionization is a topic which should be covered in your cosmology course. And again, I'm going to mention it, use it, and so on, but I'm not going to explain that in any great detail. The other topics, the topics listed in black, are something that you can expect to be covered in reasonable detail in these 21 lectures. So if you want like one image or one picture that summarizes galaxies and how they change with time, then I believe it is this. This originally appeared in a review paper about 20 years ago, but it has been used and revised and changed over the years. So this is a relatively recent version. So the idea here in this little square that you see in the image is that there are processes in galaxies that are either internal or external. So the internal processes are on the left side of this image, and external processes are on the right side of this image. Similarly, processes in galaxies could be fast or they could be slow. So the fast processes are in the top half of this square, and the slow processes are at the bottom half. So for example, if you look at internal processes which are very fast, then one thinks of protogalactic collapse, wherein galaxies form in an isolated way, but they form very, very quickly. And each of these four corners represents different kinds of processes, whether fast or slow, or internal or external. By internal or external, one means the processes where the external influence is important. So for example, merger of galaxies or an interaction between two galaxies can alter the evolution of both of those galaxies, and therefore that constitutes an external process. Something outside of the galaxy is influencing how that galaxy evolves. Those are external processes. Fast and slow, of course, refers to the time scales of these processes. We are going to come back to this big picture about 2 or 3 times during the course. I just wanted to flash it to get you started to give you a flavor for what is going to be contained in this course. Now, all of these processes tend to sort of give you the indication that things in galaxy evolution are relatively simple. Turns out they're not, they're very complicated, and they're very complicated primarily because of the factors that are listed at the center of this square, which are star formation, gas recycling, metal enrichment, energy feedback via supernovae, etc. These are physical processes that are incompletely understood at the present time, although a lot of work is happening and a lot of progress is happening. And because we don't understand these processes only incompletely at the present time, we are not able to account for completely and correctly the impact of these processes. For example, star formation. How does star formation change the internal secular evolution of galaxies? Okay, we don't know that because we don't know what exactly star formation does. When does it happen? How does it happen? How long does it continue, and so on. Once we understand that better, our understanding of these broad processes will become clearer and more focused, and so on. So a complete picture of galaxy formation and evolution has begun to emerge over the last 2 decades, but we are, I think, probably 1 or 2 decades away from having a complete understanding of what's going on. Textbooks and reference material. I cannot find one textbook that is sufficiently comprehensive and current for the large material that we are expected to cover in this course. I have put up a list of books that I am referring to again on the website. You can go look at those books. Copies are available in both the IUCAA and NCRA libraries. Some of the books can be downloaded via, for example, both IUCAA and NCRA have subscriptions to the Springer link program. So you can go online and to link.springer.com and search for Springer books, and many of the astronomy and physics books are available for download as a PDF. But thing to remember is I have put in a lot of effort to make good slides for my talks. So do use these slides as your primary reference material, and do remember to stop me and ask me questions if you don't understand something. I think that's very important. And some of the slides will cite papers which you are encouraged to read to know more about a specific topic. Okay. Are there any questions about the course content, the organization, the evaluation process? Is everything clear to you? Does anyone have any questions? This is the time to unmute and ask. Okay, so if there are no questions, let's move further. Okay, so if you look at the universe, there are three ubiquitous structures in the universe, which are very, very fundamental, and understanding them is important to understand the properties of the next largest structure. So, for example, if you want to understand stars, you have to understand how atoms operate. Okay, in fact, you have to understand the nuclei of atoms in great detail. So the atoms, of course, give rise to stars, and understanding of atoms will give you a good understanding of the properties of stars. Galaxies are, of course, made up of stars, and so understanding stars and how stars form, how stars evolve, etc., will help you understand how galaxies change with time. And understanding galaxies will help you understand how the universe itself changes with time, as on the largest length scales, on the largest mass scales, and so on. So it's very important, if you want a complete understanding of physics from the smallest scales to the largest scales, for you to understand at least these three units of matter. The story of galaxies actually has its origin in a very interesting book written in 1755 by a philosopher scientist named Immanuel Kant. And he wrote a book called General Natural History and Theory of the Heavens, in which he said that the Milky Way galaxy is like a huge solar system. It's rotating, and its origin has been from a rotating cloud. Stars far from the disk plane are not on these simple circular orbits, but on a different kinds of orbits. And disks like the Milky Way are inherently circular, but if you look at them from a viewing angle that is not exactly face on, then they appear to you as ellipses. And he said that many of the oval nebulae, which had been seen by de Maupertuis at that time with some of the finest telescopes available, he called them island universes, which means self-contained objects which were possibly rotating about themselves, containing lots of stars and gas and dust and everything else, which were essentially a universe by themselves, like an island in the universe. Nobody really understands how Immanuel Kant was able to say all of these things with the knowledge that was available at that time. Was this guesswork, or did he have some insights that we are not aware of? Nobody has been able to figure out. But it seems very, very curious that nearly 150 years before anyone else, this man, this philosopher, was able to write things all reasonably correct based on just purely philosophical ideas. Since then, of course, there were developments. In 1755 was Kant's book. In 1912, when the first astronomical spectrographs had been installed on telescopes, a scientist named Slipher discovered that some of the nebulae are rotating. And how did he discover that? Because what he found was, we look at a rotating object, then the part of the object that is moving towards you will be sort of Doppler blue shifted, and the other side will be Doppler red shifted. So he saw exactly Doppler blue shifting and red shifting of emission lines, absorption lines in galaxies. And he realized that this object must be rotating. At that time, in the 1910s, a big debate started whether galaxies or spiral nebulae and oval nebulae, as they were called, whether they were just gas clouds within our galaxy or were they galaxies by themselves. This was not a very easy debate to resolve at that time, but the discussion really became very aggressive and very pointed. In 1920, in Pasadena in California, which housed some of the largest telescopes at that time, a debate was organized between two leading scientists, Shapley and Curtis. And the topic for the debate was, are spiral nebulae island universes? Very simple question. And there was a 30-minute presentation by each of them, presenting the evidence for one side and the other. Shapley was the man who said that no, these nebulae are part of our galaxy. They're just gas clouds in our galaxy. He won the debate. So at the end, they had a vote, and they found that majority of the astronomy community in Pasadena felt that Shapley had won the debate. But it turned out that Curtis was right. So this is a lesson for everyone doing science, that sometimes just because the majority feel something is correct does not mean it's correct. It could be completely wrong. In 1925, the debate was settled once and for all by the discovery by Edwin Hubble, who later on, of course, discovered the expansion of the universe. But what Hubble discovered in 1925 and published in a paper was measurements of the luminosities of Cepheid variable stars in the nearby Andromeda galaxy, or the Andromeda Nebula, as it was known at that time. He showed that the Cepheids in Andromeda were too faint if they were to be nearby. So their faintness indicated a distance to the Andromeda galaxy that placed it well outside the Milky Way galaxy in which we live. And therefore, Hubble was able to show, using Cepheids in Andromeda and later on Cepheids in many other galaxies, that these objects were distinct entities like the Milky Way. They were distinct galaxies. And this was that seminal moment, 1925, when the field of extragalactic astrophysics was born. We are in 2022 now. We are less than 100 years old in the study of galaxies as a separate topic of research. So it's relatively new compared to stars, which have been studied systematically for about 300 years and have been known about for millennia. So what are galaxies? Galaxies are basically agglomerations of stars, dust, gas, and dark matter. Okay, so these are the four main constituents of any galaxy. Their relative mass ratio can vary quite strongly from galaxy to galaxy. But if you take average over all galaxies, you'll find that the average ratio of gas to stars to dark matter is 1:10:100. Okay. Remember, this is a very rough ratio. Okay. In an individual galaxy, this ratio could be very different. It could even be reversed. So, for example, you could have galaxies which have more gas than stars. That's possible. It's very hard to have a galaxy with less dark matter than stars, but occasionally that too also can happen. They are, as we saw, one of the basic building blocks of the universe, and certainly the best building blocks on large scales. They show a broad range in their physical properties. So if you take any physical property of a galaxy, like its mass, its luminosity, the number of stars it has, the amount of gas it has, the amount of dark matter it has, etc., it has a very broad range. In modern cosmology or observational cosmology, the understanding of galaxy formation and evolution is one of the main outstanding problems. And there are lots of people, lots of research groups across the world working on this. How many galaxies are there in the observable universe? There are about 10 raised to 11 galaxies in the observable universe. We can't actually detect all of them because the most distant low mass small galaxies are too faint to be detected with modern telescopes. But we are getting there, as we shall see in a few minutes. Their typical mass ranges from 10 raised to 8 to 10 raised to 12 solar masses. Occasionally, you can have galaxies that are a little bit below this mass limit, and occasionally above the mass limit as well. But the vast majority of galaxies lie in this range. The Milky Way is at about a few times 10 raised to 11 solar masses. So it's a relatively massive galaxy. It's not a low mass galaxy, it's a high mass galaxy. The counting and cataloging of galaxies started even before galaxies were recognized as objects that are external to the Milky Way. In late 1700s, there was a French astronomer named Charles Messier. He made a catalog of 109 nebulae so that comet hunters would not get confused them for comets. And it turns out that about 40 of these 100 odd objects were galaxies. In 1888, a new catalog was compiled called the New General Catalog that had about 7,000 odd objects, of which about half were galaxies. And each galaxy, so if you're studying galaxies, you will encounter, at least nearby galaxies, you will encounter lots of NGC catalog objects. So one example is NGC 4993, which is 40 megaparsec away, where the first gravitational wave neutron-star merger was detected in 2017. In the 20th century, as telescopes became bigger and more powerful, many galaxy catalogs were compiled. UGC catalog, the Uppsala General Catalog, the RC3 catalog are two of the most popular ones, but there are many, many others that were compiled by astronomers. Nowadays, we have automated digital surveys, which survey very large portions of the sky. The largest such survey is the Sloan Digital Sky Survey, which was carried out over the last 20 odd years and has done imaging and spectroscopy of many, many galaxies. In the imaging catalog, there are literally hundreds of millions of galaxies in the SDSS catalog, and a few million of them have also have spectroscopic observations. So if you think about all these galaxies and think how we should label them, okay, that obviously becomes complicated to give a very long 9-digit, 10-digit, 12-digit number to each of them. So what is usually done in astronomy, not just for galaxies, but for other objects as well, is to basically use the coordinates, the right ascension and the declination of these galaxies to create a number that is used to label them. And that, of course, has the advantage that when you know the number, you also know which part of the sky that particular object is. Over the next decade, which means from starting about 2 years from now and then going on for a decade, are very large surveys like the Rubin Large Survey of Space and Time, which is basically a synoptic survey, which means it will observe the same part of the sky multiple times. Typically, it will cover the whole sky twice in 1 week. And it's going to provide photometry for 10 raised to 10 galaxies. And remember, I told you that there are about 10 raised to 11 galaxies in the observable universe. And we are going to be able to see about 10% of them with this single survey. And these will include galaxies which are very close by, part of the local group, to extremely distant galaxies at redshifts greater than 6. This particular survey will also provide useful shape measurements and 6-band photometry for 4 into 10 raised to 9 galaxies, very, very large numbers. So in any process, whether it's botany, zoology, or galaxies, the first step is the census. The second step is the classification. And these are common steps in any empirical science. In 1936, Edwin Hubble wrote a popular book called The Realm of the Nebulae, and he proposed a scheme for classifying galaxies. He called it the tuning fork diagram. And this particular scheme survives in its essence up to the present day. And in this course, you are going to encounter this particular diagram, his Hubble scheme for classifying galaxies, several times in this course. So the main types of galaxies seem to be what are called ellipticals, what are called lenticulars, what are called spirals, and what are called irregular galaxies. This is an approach that developed when imaging or photography were the main ways of identifying and studying galaxies. But nowadays, we are able to do multiplexed spectroscopy. We are able to do spectroscopy on many objects at the same time. And therefore, we can use a different mode of galaxy study, where we can look at the properties, at the kinematic properties of the subsystems within galaxies. And now, instead of defining a subsystem by its morphology, that this is a bulge, this is a disk, and so on, you do this via the kinematic properties of these objects. So fast rotators, slow rotators, halo, rotationally supported disks, and so on. And use that to deduce their origins and constrain their evolution over time. So why is galaxy classification useful? It is useful because these classes bring order to the diversity of galaxy forms, and they span and include a majority of galaxies, as we shall see. Their unambiguous and easily identified criteria are used in the classification of galaxies, and the classified types are related to important physical properties. They provide some insight into the internal processes behind the formation and evolution of these galaxies. If you look at classification of galaxies in the traditional way, you will find that optical imaging was the method that has been used most often to observe galaxies and to classify them. Since optical imaging is a very relatively cheap process in terms of the amount of telescope time that it needs in order to get very sensitive images, it's very widely used. Optical light is also very sensitive to emission of light from stars, and also in absorption to the dust. So if there's a lot of dust absorption, you will see all the starlight getting absorbed, and from that you'll be able to deduce how much dust there is. Today, there are, as we shall see later on in this course, there are many other criteria such as color indices, spectroscopic parameters based on emission and absorption lines, the broadband spectral energy distribution of galaxies. So there are galaxies with and without radio emission, with and without X-ray emission, And these are also used to classify and group galaxies together. So for example, the study of radio galaxies is a very active field of research for many people in NCRA and in radio astronomy in general. So, so I'm going to stop here. And if there are any questions about what I covered today, or if you want to go back and you have any questions on the course evaluation, organization, etc., then please speak up.
Hello, sir.
Yeah.
Sir, how did you get that number of galaxies in the universe is 10^11? I mean, how to count it?
How do you count it? Okay, that's a very interesting question. So, so first of all, you know the concept of the observable universe, right? There may be galaxies which are so far away that the light from them has not yet reached us, because the universe is only 13.7 billion years old. So if you have objects which are so far away that the light will take longer than that time to reach us, then they're unobservable. We can't see them, right? So the observable universe is a finite sphere of a certain radius. Now, how do we estimate how many galaxies there are? This is not a very easy process because of two things. One is the universe itself is evolving. So new galaxies get formed. Sometimes galaxies merge with each other. So two galaxies may merge with each other together and form one galaxy. So your galaxy count has gone down. New dwarf galaxies may be forming at any given point in time, and so on. But now over the last 20-30 years, we have gained a good understanding of how galaxies evolve over time, over almost the entire lifetime over which galaxies have existed, right? And we have a good census both through observations. We have a comparison between the observations and the theoretical predictions of large-scale structure formation and formation of galaxies. We also have a lot of numerical simulations of galaxy formation, all of three of which are reasonably consistent. Okay, so when I put down 10^11 galaxies, I put a tilde in front. Maybe it is 2 into 10^11, maybe it is 0.7 into 10^11. We can't be sure exactly how many galaxies there are in the observable universe, primarily because at the high redshifts, the faint galaxies become observationally invisible, because the low mass galaxies will be very faint, and even with a very sensitive telescope, you will not be able to see them directly, right? So you will miss, you will undercount. So what people do, of course, is that they correct for this kind of bias by saying that, okay, in the nearby universe, we know how many low mass galaxies there are. And we have some understanding how the luminosity function of low mass galaxies evolves. We can extend that, extrapolate that to high redshift, and we can predict how many low mass galaxies there must be, although our telescopes are not sensitive to detect them. So it's a little bit of a complicated process, but you can say that it's accurate certainly to an order of magnitude, but it may be inaccurate by a factor of 2 or 3 quite easily.
Okay, thank you, sir.
Yeah. Any other question?